One of the things we saw in the last video was the definition of pure strategies for an infinitely repeated game, namely that a pure strategy is going to be a function that tells us what to do given any finite list of any finite list that's what happened up to this point. What I didn't say is that that kind of space of strategies is extremely hard to understand. In a sense, there are too many strategies. This includes a lot of crazy things like uncomputable strategies that we'd really like to rule out. So in practice, we usually restrict the strategies that we're allowed to consider for infinitely repeated games to what are called finite state strategies, which are significantly easier to understand. So what this means is that we're going to bound the memory of the players. We're going to only allow them to remember a finite amount of information. So they can't just keep absorbing knowledge of the history forever as the play goes on and on. So this is it's a bit of a questionable point whether this counts as imperfect recall or not. So officially, the game itself still has perfect recall, but we're strictly only allowed to use forgetful strategies. But this is kind of equivalent to modifying the game itself to become imperfect recalled. Okay, so a finite state strategy. So instead of just being a function from an arbitrary function from lists to moves, a finite state strategy is going to be given by a finite set of states that player's memory can be in, together with a choice of an initial state. It's going to have a readout function, which says, given the current state, what move should we play? And then a transition function that says, given the state that we're in and what moves the other players have just played in the current stage, which memory state should we go to next? So these things are state machines. So if you've ever studied computability, if you did an undergrad in computer science, you've definitely seen these things before. So this is old news for you. If you haven't studied computer science, you may not have seen these before, but they're pretty straightforward. So we can draw these things as basically graphs. By the way, the keyword here, there are different types of state machine. The keyword here is this is called a Moore machine. Okay, so we're going to draw a graph which has like a node for each memory state. So here's the definition of a strategy for infinitely repeated princess dilemma, which is called tit for tat. This is probably the most famous strategy for that game. So the idea of tit for tat is that in the first round we cooperate, and then afterwards we repeat the opponent's last move back at them. So what that means is if the opponent cooperates, we cooperate. If the opponent defects, we defect, and we kind of just parrot them, but one stage in the future. So to do this, we need two memory states, aka one bit of memory. Namely, we need to remember whether the last move was cooperate or defect by the opponent. So, so we have two states, and I've labeled each state by the readout. So this says that if we're in this state, we cooperate. If we're in this state, we defect. This arrow coming from nowhere, this conventionally says what is the initial state. So this says that initially we're going to be in the cooperate state, so we're going to cooperate in the first round. And then these arrows are labeled by the opponent moves. So this says if the opponent, if we're in this state and the opponent plays defect, then we're going to transition into this state, which means in the next round we're going to defect. So you can see that I've set this up so that whatever the opponent does, we're going to transition into the state that says that we're going to read out the same move in the next round. Okay. Here's another strategy. This is Grim Trigger. So this is the strategy that I showed you in the last video, that says cooperate if the opponent has never defected, so in particular initially cooperate, and if the opponent ever defects, then we defect for all time. So you also need one bit of memory, aka two memory states for this. So we have a cooperate state and a defect state. initially we're in the cooperate state, and as long as we're in the cooperate state, then if the opponent cooperates, we stay there. If the opponent ever defects, we're going to transition into this state. But once we're in this state, we're stuck. We can never get back. So even if the opponent cooperates, we're going to just stay in this state, which means that no matter what, we're going to keep defecting. Okay. We can also have strategies which will punish the opponent defecting a finite amount. So tit for tat is equivalent to 1 round of punishment for defecting. But we can in general have a strategy where if the opponent defects, then let's say for 10 rounds we will defect, and then after that, if they haven't defected again, we're going to return to cooperation. So doing this needs n+1 states to do this countdown. So we're basically going to count down the number of rounds that we still have to punish the opponent. So this needs about log n bits of memory. So I've drawn here initially. So this is I guess 3 rounds of punishment. So initially we're in a cooperate state, and that goes to itself. But we have 3 other states in which the readout is defect. And so this is like ticking down the timer until we return to cooperate. So if the opponent cooperates, we're going to kind of tick down the timer. If the opponent defects, we're going to reset the timer to the maximum. Okay. So it turns out that, so I've given you a bunch of strategies. So each of these defines a strategy for iterated prisoner's dilemma. And it turns out that every combination of these turns out to be a subgame perfect equilibrium, provided the discount factor is large enough. So there are actually lots of ways to cooperate in prisoner's dilemma. So I'm going to note we technically haven't defined yet what is a subgame perfect equilibrium of an infinitely repeated game. So the next video is going to be about that. So this is kind of a spoiler. But what you'll notice is that all of these strategies that I've just shown you will initially cooperate, and they will only defect if the opponent defects first. So what that means is that if you play any combination of these against each other, they will always cooperate. They only defect in retaliation, and so they have nothing to defect against if they play each other. So what that means is that infinitely repeated prisoner's dilemma is going to have a bunch of subgame perfect equilibria, which, if you play them, result in cooperation. So that is to say, the players are going to get a higher payoff than they would if they were just playing a finitely repeated game. Because in finitely repeated game, we only get 1 subgame perfect equilibrium, and that is defects in every round. So in the next video, I'm going to make this precise by saying what actually is a subgame, what's the subgame perfect equilibrium in an infinitely repeated game.